Hello everyone, welcome to our event. This event is brought to you by Data Talks Club, which is a community of people who love data. We have weekly events, and this is one of such events. So if you want to find out more about the events we have, there is a link in the description. Click on this and you'll see everything we have in the schedule. Then if for whatever reason you have not subscribed to our YouTube channel, do it now. You will get notified about all our videos. And then we have an amazing Slack community. Join it. You can hang out with other data enthusiasts. We also invite book authors like Serg. Serg was I don't remember when was it, like half a year ago, 8 months ago. So Serg was answering questions about his book. So yeah, do join our Slack. And then another announcement. We have a free course about MLOps coming soon in a couple of weeks. So there is also a link in the description. Check it out if you're interested. And then finally, during today's presentation, you can ask any question you want. There is a pinned link in the live chat. So just ask your question there. And then probably at the end of the presentation, we will cover these questions. Or is it okay to interrupt you if there is a question relevant to what you're talking about?
Sure. Okay. I mean, as long as it's not too long of a question, it's fine.
Yeah. Okay. But I'll probably keep most of the questions till the end of the presentation. So that's all from me. Now the floor is yours. Yeah, thanks for joining us today. So looking
no
forward
problem.
to
I'm glad to participate with your vibrant community. Yeah, it was great to be part of the book of the week. I think it spawned a lot of nice questions that were a joy to answer. And so I hope I get the opportunity again of doing that with this presentation. So let me share my screen. All right. So it's actually going to start with a presentation, and then I'm going to move forward with the code. The presentation is kind of short. So mitigating bias with the explainable AI toolbox. So before we begin, let me quickly introduce myself. My name is Serg Masis. Serg is my English nickname, but you can call me Sergio if you speak Spanish. That's how my name is pronounced. I'm a data scientist at Syngenta, where I work on food security problems for the Climate and Agronomic Decision Science Department. And a year ago, well, actually about 2 years ago, started writing a book for PACT, which is a comprehensive hands-on overview of interpretable machine learning. It was released last year and it's available on Amazon. This is actually my second career. For over 10 years, I was a full stack web and app developer and a webmaster, and even the founder of a search engine. In these roles is how I got into analytics. Since the internet is often the source of big data. So without further ado, let's dig in. This session is broken into a couple parts. First, what is XAI and interpretable machine learning, and what is fairness and the origin of bias, and then we'll move on to the code. I suggest that you guys go to one of these two links over here.
Can you share the links, please? I'll put them in the description.
Oh, absolutely.
Just send to Zoom.
Hold on. I will. Hold on, chat. I'll send those. Probably should have sent them to you before. So I'm typing them right now. 2022. Okay, this should work, and this will send it to the first one. Yeah, you can copy it into the YouTube. Yeah, that will send you to the Google Cloud, Google Colab, and then the next one. I keep trying to grab it. The other one is hold on, GitHub.com.
Are you actually typing it?
Yeah, because I can't copy and paste it while I'm presenting. I should have taken care of this earlier. All right. There.
Yeah, adding this as well.
Yeah. All right. So you have the links. So please go to the collab or, go through the longer process of getting a clone of the Git and then install the first, run the first three cells, the one that says install libraries, load libraries, and then loading the data set. That's all. I mean, that will just make things quicker later on. Right. All right. So many of the questions asked by attendees in previous presentations have led me up to believe that I should start off with what exactly is explainable AI and interpretable machine learning and how they relate to fairness. There seems to be some confusion here, so I added this section to clarify that. First thing to know about these terms, that they're mostly the same thing. One stems from academia, another more from industry, but they're used interchangeably. I prefer the term interpretable machine learning. Um, However, explainable AI um, is also a good term. The second thing to know is that they have been increasingly more popular over the last 5 years, as evidenced by these Google trends. Likewise, during the same period, there has been more and more mentions in books for both terms. However, the vast majority of these books have been either non-technical books for a business audience, books about AI ethics, or academic compilations that are very, dive really deep into the subject. Practitioner-oriented books on the subject have been very scarce all these years. My book, published last year, was only the third one. Thankfully, by the middle of this year, there'll be six more books um, on this topic. So, what exactly is interpretable machine learning? I mean, the main concepts are fairness, accountability, and transparency. A lot of people focus on the bottom of this pyramid, which has all these concepts, but the parts on top are very important as well. There are many concerns associated with concepts grounded in ethics, which you see here. And ultimately, what we want to know is, can we trust the model? Since trust is mission critical. So it's fair to ask, is interpretable machine learning and ethical AI the same thing? Not really, but both concepts overlap. Ethical AI, also known as responsible machine learning, encompasses much more than interpretable machine learning because it includes like data and algorithm governance aspects, things like privacy regulations, data management procedures, and even modeling standards. And they're supposed to uphold the same things like fairness, accountability, and transparency. On the other hand, interpretable machine learning or explainable as AI is how we implement the FAT principles with machine learning. In other words, how does a machine learning practitioner do that? And it can be used for ethical reasons, but it can also be used for unethical reasons. Like an example I give is we have adversarial robustness tools that can be used by a perpetrator to actually, um, spy on a competitor with these tools, or to sabotage a competitor as well with the very same tools. So they can be used unethically, and they also can be used with no ethical reasons in mind. So. Now, next we'll talk about what exactly is fairness and the origin of bias. And fairness in particular, we all have a concept of what it is, but I mean in terms of machine learning. So there's three notions of fairness. There's treatment, process, and outcome. Um, and and generally, like unless robots are interacting directly with us, only the last two pertain to machine learning. Uh, because treatment from a machine learning uh, entity or AI system in general, it's not something we generally experience, at least directly. So first, there's outcomes. In other words, predictions being balanced from a statistical point of view. Um, and then there's a question of having a fair process. And algorithmically, this may mean many things, but I prefer to see it as no double standards, like having the same procedure across, you know, like a population or a sample that has the same kind of characteristics, and there's no reason to treat them differently. Um, Fairness in practice for machine learning is balancing act between procedural and outcome fairness, since they're sometimes they're mutually exclusive. So why focus on fairness? When you hear explainable AI, what comes to mind is explainability and interpretability, which is the base of this pyramid as transparency. But as complicated as this may be, the base level of the pyramid is actually the low-hanging fruit. And the farther you go, the harder it becomes, while being less in top of mind for machine learning practitioners and more important for the general public. Because when the general public hears about, a responsible AI and all that, they're thinking of other things. They're thinking of the privacy of their data, having fair, treatment by the models. So I thought, well, let's begin at the top of the pyramid where unfairness is manifested as bias in the data and corresponding predictions. And we don't really skip other steps because the top layer really depends on the bottom. You really have to understand the model well, and you have to have a consistent and robust model to be able to be fair to begin with. So what is the origin of bias? In supervised learning, we derive meaning and predictions from a model that's supposed to represent the truth. We really make a big assumption that this data accurately depicts the truth. But the most fundamental problem we're aware about is bad data, typically data entry errors. They're random if we're lucky. However, there's also biases associated to bad data we should control for, and anomaly detection methods and comparing with external data sets for issues in distribution can help correct these issues. Uh, as for the truth, we have a whole host of issues. First, we have the ugly truths, all the prejudices and systemic biases that exist in the world, and our data is merely depicting. And we can make sure our models mitigate them. Our models don't have to reflect the truth that exists, they can reflect the truth that we want. We also have fake truths, which are the many ways models can be purposely tricked, and truths that change over time. All these issues only aggravate data issues. So lastly, we have our own biases with our models. Chief among them is observer bias, which we blind ourselves to what we assume or want to be true. Not all these biases lead to unfair outcomes or procedures, but they easily can. Having a data-driven approach to machine learning can go a long way to mitigating them. So it's easy to blame a complex model for bias, but a model, whether black box or not, only amplifies bias that already exists in the data. Therefore, detecting and mitigating bias should be performed primarily to the data and throughout the machine learning workflow to ensure that whatever remains is not amplified. All right, so I'm going to stop the presentation and I'm going to continue with the this. Hopefully you all got settled in and you got the links. And so now I'm going to run through this. So first thing first, well, I didn't follow my own advice. So, well, it's probably going to tell you this. You run anyway if you're doing it through the Colab. Um, then load the libraries, then load the data set. Okay, while that goes on, I'm going to explain the first rows and explain what this data is. This is the X and the Y. Hopefully, I don't have to explain what this means. This is the label, and this is the data set, the rest of the data, the features. So here you have, as part of the index, you have things that are, protected features. You have race and sex. Generally, you don't want to include them in the data, but you want to control for them when they're protected. Sometimes age is a protected feature, but in this case, we've chosen to not make it a protected feature. There's also, work class, there's education. Again, these could be sometimes protected feature. Education, the number of years they've been educated, which corresponds to this education category. The marital status, the occupation, the relationship, and capital gain, capital loss, hours per week, and native country. These will be removed logically. And then let's see. Yeah, it's all loaded now. So, and just for consistency, I'm going
Just
to just
a quick
continue running this.
question.
Yeah.
What does it mean for a feature to be protected? Does it mean that we do not use it as a feature, as an input to the model?
Well, generally, what that means is that we're going to check if there's bias for it. If there is, we'll make sure that there's some kind of balancing going on to account for it. Protected just means that we're going to account for that, that we're going to control for that.
Okay, so we need to keep
And
an eye.
and it might mean in many cases it means we don't use it.
Okay.
Not always. Sometimes there's a good reason to use it, but you have to do it carefully. And the reason you would use it is to kind of align the model to it. So we're going to discuss this further, but there's methods that leverage machine learning, and you can align a protected feature with the outcome. You can use like some adversarial method to kind of correct for that. So it can be useful to include the feature. Um, so we're going to check how imbalanced it is. First, I haven't explained, I skipped one step here. I haven't explained what the labels are. The labels are the level of income. So it's a binary feature. Well, here you see it as a category, and it says if they make less than 50,000 or they make more than 50,000. So folks that make more than 50,000 a year are roughly 25% of the data set. And we can see there's different ways of seeing how this is distributed. Just so you see what I'm doing here, I'm just taking I'm taking the gender and the annual income, and then I'm gonna group that and divide that. So then you can see how it's distributed per each one of these genders. So you see like females that make less than 50,000 are roughly 89% of all, within their own group. So 89% of females like make less than 50,000, and those that do are roughly 11%. That those that make over 50,000, and for males, actually, yeah, males are far more likely to make more money. So you see here 31,000 versus 69,000. That's 69,000. 69% versus 31%. Never mind. You can see this graphically with this plot. So here you see this is a proportion, uh, males versus females. Like this is the 11% we were talking about versus the 88%. And this is the 69% versus the 31% within each group. Logically, there's also an imbalance on another level, which is, there's more males than females in the data set. So some of the data preparation steps we'll do, we're going to join X and Y. We're going to encode the indexes for X and Y. And then we're going to define a seed for reproducibility. This is always important to do. And I keep this as a variable, and I make sure I put it in every kind of every place that it is an option. Like as you might know, maybe you don't, but train test split has that option. As you see here, random state. So we can place it. So we're going to one hot encode our features and this save the originals for test and train. And then we're going to do the one hot encoding. And so this is the data already one hot encoded. There's a lot of categories in there. Then we're going to quantify the data set bias. So let me explain what these mean. Like these are different measures. There isn't an agreement. There isn't like a perfect measure for data set bias. There are many. So The statistical parity difference is if we're taking what is regarded as unprivileged versus a privileged, uh, and in this case, the privileged gender is male and the underprivileged gender is female. So what it's going to do is just measuring the difference between one versus another in terms of its likelihood of having a higher income. In this case, females are 20 points less likely to be, have a higher income. So in this case, like the reference point for statistical parity difference is zero. Zero means perfect parity. So anything in one direction or another means that there's no parity. So in if it were a bigger number, it would mean a favorable towards the underprivileged group, which is usually not the case. And then if it's negative, it means unfavorable. And so that's what it's measuring. The disparate impact is kind of this very similar, but instead of being a difference, it's a ratio. So you have between 0 and 1, and the closer to 1 means better, means more favorable. And so since it's a ratio, that's what you expect. So it's not it's still bad because it's over 0. No, it's under 1. That's in other words, it's under 1. 1 would be perfect parity in this case, being a ratio. All right, so now I'm going to define some utility functions. I have one for evaluating the classification model, and one to compare two confusion matrices. And that's pretty much all they do. This just makes things a lot easier. First, we're going to fit a logistic regression model. So this evaluate class model function will yield the following outcome. And as you can see here, there's a confusion matrix. So the number on this corner is the false positives. The one here is the false negatives. This is the true positives and true negatives. So this is something you have to take in mind in cases like these of imbalance and check between both and see which one is better. In this case, in the terms of fairness, this is pretty important because disparities in one may not mean the same for another. Sometimes you're willing to overlook disparity with false positives versus one with false negatives. So it depends which one is the most negative thing to have here. In this case, you rather have false positives than false negatives. So now we're going to do the cat boost classifier. This should yield better results as far as this goes. Here you see, just for reference, accuracy is around 84%. No, yeah, 84%. And then precision 73, let's say, and 57%. So see if that improves. Yeah, it is better on all metrics, I think. 57, yeah, it's better in all metrics. So that's another thing, that you have to take into account when you're dealing with this. Sometimes the knee-jerk reaction is a simpler model is more fair, and that might be the case from a procedural standpoint, but from a statistical outcome standpoint, you want good predictive performance because bad predictive performance is bad for everybody. The thing is also the complexity of the model can come with some imbalances. It can amplify the bias more than a simpler model would do, but it's not always the case. So there's many ways.
Sorry, just a quick question. So here you see that this bias is this MCC thing, that MCC test, or so the larger it is, the less biased it is, right?
No, MCC is called the Matthews correlation coefficient, and it's just a
Ah, okay.
different way of measuring the
I see. So it
the
has nothing to
balance
do with
between all parts
bias.
of the confusion matrix. No, not exactly. What it is, it's well, the F1, for instance, the F1 only really cares about, precision and recall. So it's like an average between precision and recall. MCC takes a more nuanced approach, and the way it's calculating, it's taking into account like all parts of the confusion matrix. So if you have an MCC of over zero, I mean, it means the model is predicting well. Zero is like
Mhm.
like the coin flip, um, number.
It's
In other
another.
words, it's a useless number. And the closer it is to the one, the closer it is to being a perfect
Mhm,
classifier.
mhm,
Um, and it's a little bit. I like it because it's more nuanced than the other ones.
mhm.
Sometimes if I cared to have like a perfect ratio between false positives and true negatives, then MCC would be a great metric by itself. But in this
Yeah.
case, since I want more than one another, it's okay to shoot for a good MCC, but it's
Mhm.
not as important as shooting for a good precision or recall.
Yeah, because you mentioned that like simpler models could be more fair than complex models, and I was wondering if this was the observation you did based on any of the output or outputs here that you saw, or just in general.
No, just in general, from
Uh-huh.
but that's only from a procedural standpoint. I was saying
Mhm.
like simpler models, given that the procedure is simpler, they might lead to more fair outcomes. Like if you say, well, say you had a model that was like predicting who's gonna pass um, the bar to become a lawyer, right? You probably say, okay, well, like the ones that have the highest grades are probably more likely to do better on the test. So if you were to kind of use that and kind of to say, okay, well, I'm going to give scholarship to the ones that are more likely to pass the bar once they graduated, then um, then you might just a simpler model might do in that exercise because you just have to tie a couple of grade variables monotonically to the outcome. That's all you have to do. So you just need some kind of model that connects those two things and make sure they're aligned and there's not a lot of non-linearity that you would maybe find in other cases.
Let's see. And if
So
you train
it
this
would
similar model with cat boost, then good luck figuring out why it made this decision.
exactly,
Right?
exactly. So there are cases in which you want to use that kind of procedural connection because it just seems more fair. It could be the case also with criminal law for in a lot of different realms. It might be the case you want something simpler, but uh, if we think of what this is for, maybe it's for we don't. I'm not kind of detailing what it's for because I don't know, but if you're going to tie income or try to predict income, it might be for like marketing purposes, you know, who you're marketing a newsletter to. Um, so it might not be that bad, but maybe it's for something else. Maybe it's for like the government to kind of you know, it might be to benefit people that are lower income, or it could be to benefit people that are higher income. So it really depends what it's for, who what kind of metrics are best for it. Because you, it's not only a question of seeing who's underprivileged and who's privileged, but it's also a question of seeing also what kind of benefit or disadvantage is given to that group. Like in a hypothetical case that this is to maybe offer credit cards to someone if they make over 50,000 or you assume they make over 50,000, then uh, you definitely want to check for the false positives. You want to make sure that women aren't more likely to get you know uh, no, you want to make sure they don't get more likely to get false negatives. So it really depends. So to continue on this process, first thing we want to do is to check if Ismail is, make sure we have like a binary kind of, what is it, array. or list. So I think this would be a list, in which it's when it's one, it tells us it's male. So that's so we can then go here and we can just subset these arrays. So we're going to run this function that what it does, it just simply compares two subsets and kind of it generates like confusion matrix and put them side by side. So it's a very simple function, but that's all it does. So here we see how there's disparity, right? They're not like the story here is like this won't tell you all the story. You can have a confusion matrix for the entire like data or test data set, but it doesn't really tell you how it performs on when you splice it up into different groups. So here I'm splicing it up like this, and something you notice is like there's a big difference in the ratios between all of these. It's far more likely to get false positive, false negative in the case of females. And when you compare the false negative rate between both, you see, well, it's 28% higher for females than it is for males. And that should tell you something. In this case, like let's assume the case of, it being to offer credit cards or to approve credit cards based on this assumption of how much they make. Um, you know, maybe it's not a requirement to disclose that or, upon an offering. So like this is kind of bad because, you want to include as many females as it is fair to include them. So
And the reason we look at false negative is because the way we use the model, let's say if we use it to make a decision whether to give a loan or whether to give scholarship, right? So false positive means that we reject somebody, right? So we do not give scholarship to somebody, right? That's
no,
why.
no, because in this case, the positive class, I probably should explain this. In this case, the positive class is that they make the higher income.
Okay. Yep. So then we say that if it makes a false positive. So I'm just trying to understand why exactly we look at false positives, not at false negatives.
No, we're looking at false negatives. This is the
Just,
false negative rate.
yeah. So why not false positives?
Well, a false positive means we're offering we could be offering a female or a male or whoever it is an advantage that they're not that they shouldn't be getting. They shouldn't get the offer for the credit card, given that they don't have the income for it. So in this case, a false negative means that and people with that don't have that income are going to get it.
Hmm.
My as long as I'm let me see if I check that. Sometimes we've seen this for a while. False
It
negative.
looks like both are interesting, right?
Yeah,
Like looking at
yeah,
both ratios could tell us something.
yeah. I mean, we could definitely see the other ratio. Let me see. I just ran this. So you can easily take this. And let me see the other one.
So it could be maybe for males they get a chance more often but when they don't deserve it, right?
Yeah, yeah. It is the case. Wow, it's a lot higher. You're right. There is a big disparity there. Males are advantaged also on false positives, and much more than false negatives.
Mhm.
So this is how I compute the false negative rate. It's just the false negatives over the false negatives and the true positives. So so it's false negatives over the false negatives and the true positives. So this one over these two. So let's quantify model bias here. It's not the same thing to quantify data set bias than model bias, because with model bias, you're doing it over the predictions, not over the labels. So this is for logistic regression. So it's still 18%. on the negative side, 18% like disadvantaging females, and this is for cat boost, 17%, so it's a little bit less. And of course, this means that this predict impact is closer to one than it is for logistic regression. So here we can see that, yeah, indeed, cat boost is advantages females a little bit better than logistic regression. So let's look at how we can mitigate it. So there's many methods to mitigate bias. So there's pre-processing, in-processing, and post-processing. The difference between pre-processing is done on the data itself. In-processing is done during the training process, and post-processing is applied after the fact to the predictions or to the AI system that kind of is supposed to kind of output those predictions. So here we have this method called reweighting. And so reweighting, what it does, it creates some it creates like what is sample weights. So I don't know if you've used sample weights before, but there's something you can just add. Hold on, let me see where I put it. Maybe I didn't use the same one. Sample weights. Yeah, so sample weights are added to each in the fit process. So you can add them to every you can add them to during the fit process. And let me show you how it shows up. Well, first I'm going to calculate this. So it's minus 18. It still hasn't improved quite a bit. Let's see, 34. But the disparate impact is higher this time. So this is how it works. So you
Yes, the
create the
higher the
sample
better,
weights.
right?
Hmm?
The higher
What's that?
this disparate impact, the higher the better, right? The less biased it is. Do I remember it correctly?
Yeah, the less that the bias is.
Mhm.
So I'm generating the sample weights here, and you can see here the sample weights. There's one for per every observation. So they basically are a weight that's imposed during the training process to every sample. And something you can see, you can verify this. You can take the sample weights and you simply get the mean for them. And the mean should be, if it's not one, it should be really close to one, because one is the default. But if you think about it, the default weight to each one of your samples should be one. But here it's really improving the training process by simply applying a weight to every sample, every observation. This is an in-processing method. It's called adversarial debiasing. So here we're going to fit the model with, and it uses, I believe inside it uses a neural network. It uses TensorFlow. So the way adversarial debiasing works is it leverages two opposing actors. It has a predictor and an adversary. So it kind of, that adversary just penalizes every time it predicts based on the protected feature. So it knows it's based on the protected feature because if it also predicts using the protected feature. So we're going to train with that, and we're going to see how well it does it. Well, I kind of have the answers here before the fact, but it does improve things quite a bit. You can see here it's the disparate impact is all the way at 70%, and the statistical parity is now reduced to close to 6. Well, -6, I mean. So this might take a little while because it's a neural network. Um, so I'm just going to go ahead while this happens and explain the post-processing. Okay. So something you note, and it's important to think about, some of these fairness processes, they have an impact, as you can see here as well, on accuracy. So it took a hit of like 4% in accuracy. Also, recall and precision took a hit, but that comes at the cost of improving fairness. Sometimes if you apply, because you apply these bias mitigation procedures on each one of the steps, you manage to counter that. So like if you, I'm doing, and for this exercise, I'm doing them separately, but if you did one pre-processing, one in processing, and one post-processing method, um, you might achieve almost or the same predictive performance as if you didn't do any bias mitigation. So here we can see the improvement. For post-processing, there is we're going to combine it with pre-processing as well. So here these methods are done exactly as I said before to the predictions. So there's one called calibrated equalized odds preprocessing. So this does not change the labels, but it changes the scores. So they're an average equal, and this is what's called calibration. Sometimes you just want to change the labels, but uh, it's often useful to have scores that kind of match that. So when possible, I recommend to do calibration. So this constraint is interesting because it can't, when you're dealing with the scores, you're calibrating the scores, you have to tell it you know, what you want to optimize for. Because there's nuance there, as we saw earlier. Like one thing is to say, okay, well, I want to shoot for a good, parity with the false negative rate or the false positive rate, or with precision or recall. They might be conflicting in the sense that if you're optimizing for one thing, you're definitely not going to optimize for another. So here the constraint we have is on false negative rate, but we could definitely change it to something else.
I'm trying to understand this pre and post processing. I'm not sure I understand. So pre is we prepare data before we fit with the model, right? And post
Yeah,
is okay, we already have a model, we have some predictions. How do we modify these predictions in order for the model to be more fair, right?
yeah, exactly. Sometimes, as you see here
Waiting
with
is
the sample
pre-processing.
weights, the sample weights are a method. It's interesting. Usually, pre-processing methods will modify the data. In this case, it's not modifying the data; it's just modifying the 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 weight you assign to every observation.
But
That's
what practically it does, it's like it's sort of resampling, right? So we make sure that both
yeah,
like both females and males in this particular example, they have equal weight in the model. So they see
yeah.
like maybe these examples will
Exactly.
give them
It does
equal
that through a different
chances.
means. You could do upsampling, downsampling. All of these are pre-processing methods. And
Mhm.
they're ones that are more sophisticated that actually change the data, something about the data. And those I recommend to only do in like very severe cases, because usually you don't want to change the data because it just makes harder for you to kind of trace back. If you ever have to compare something, you have to have the original data set as reference. Um,
There is a question related to the triangle of fairness,
yeah,
and the like. I don't, to be honest, I don't remember this triangle. Maybe you have it somewhere close to you.
yeah,
And the question
yeah.
is, are these pre, in, and post processing related to this triangle?
Let me see. I, yeah. They're mostly, to be honest, they're mostly related to this one. There are some methods that align better with procedural fairness. One of them is, as I discuss in my book, is monotonic constraints. It's not discussed enough. There are models that their nature is monotonic. So you have a linear regressor, it's linear, so therefore it's monotonic. Um, there are others in which you can't assure that. You can't assure that you do a partial dependence plot or anything like that between a feature and the outcome, and you might find something, all over the place. Now that might be like completely counter to your mission, and it might be completely unfair, like we were discussing about, aligning grades to scholarships. So, like, like if you ask anybody, you say, well, you know, if we're going to give a scholarship to something, what are we looking for in that candidate? You'll say, well, someone that can prove that they can study. And how do you prove that? Through grades. I mean, some people may not agree with that, but you know, generally you'll want to align both things and make sure that the likelihood of getting the scholarship is tied to the having good grades. So that you would have to, if you use a very simple model, it might be like baked into the way the model is. If it's like say cat boost has monotonic constraints, so you can definitely implement a fair procedure through doing that. As far as like uh, fair outcome is, there's like a lot of methods that deal with that, and pretty much all throughout this session, all the methods I've been discussing are more focused on the outcome. They're more outcome oriented, because procedure, like you could use, like for instance, to make sure that things are fair or intuitive. Procedure wise, you could use causal modeling. You could use different kinds of statistical learning for that. I mean, but we're focused more on this. So no problem. Here I did the calibrated equalized odds, and I also did the at the same time the sample weighting, and this is a case in which using both did not yield better results than just using in processing, but it used it by doing pre-processing and post-processing. I got better results than using either one independently. So perhaps if I added the third one, if I added also adversarial debiasing, I would get even better results in that. So here I'm going to compare them. So here the FNRs are reduced to just 1.07. So that's quite good if we compare it to the beginning. Um, had we been shooting for false positive right now, I'm wondering, what we'd be getting. But yeah, you're free to take this and do whatever you want with it and change all those things and play around with it. So now I'm going to go ahead and compare the results. Um, so this library called XAI is not maintained very much, but it has some very nifty like graphical tools. Unfortunately, the people that made it are not maintaining it very much, at least in the last 3 years. So uh, that's a frustration. Sometimes you find a very good library and people stop maintaining it. Okay, so here we're going to take this. We're going to iterate across different protected features and see how well the models do. So here we have, the race dimension, and this is the female male dimension. And this is not something we discussed in this session, but it race is also one of the protected features. And one of the things that is complicated uh, is is measuring disparities across different protected features at the same time. And um, there are some metrics that do that. But there's a lot of things that become part of the discussion. You know, Simpson's paradox. Intersectionality between groups. How deep can you go? How many different protected features is it reasonable to include in something like this? So here's the before and by the way, this is the precision recall plot. If you don't use it, it's like the number one plot you should use for imbalanced classifiers. So here's for race. This is for gender, and this is the after. So we're just going to eyeball this. It'd be good to put them side by side, but we're going to eyeball it. Strangely enough, it did improve things for race. As you can see, the gap between the orange and the blue is much lower, and for female and male, look, it's almost aligning completely. So this is what I was shooting for. This is what I was trying to close on by focusing on the false negative rate. But there's many ways to do it, and it really depends on what it is used for. This very same data set, it was applied to a different problem. You know, it might you might have a different way of dealing with it. Like I said, I mean, hypothetically, if this was used for like the credit card scenario, this is the best way to do it. But if it's for like social assistance, then you might want to do it in a different way, and you might want to focus on a different metric. So.
Is it a must that we do not use them as features here in this case? I'm wondering how these plots would look like if we, let's say, included gender as a feature.
If we included, well, we could do the experiment for sure. Add gender as a feature. It probably be more biased. That's my suspicion. Um, there is the concept of fairness through awareness or unawareness, which means the model is either aware or unaware of a feature. But bias is tricky because it's not by removing the feature itself that you necessarily remove it, because it's correlated. It's not only correlated to the label, it's correlated to other things, other features. So if you look deep into it, you might realize, well, what are females less likely, to have or not have when you compare the males against all the other features? Are they more, are they more likely to be married than never married? Are they more likely to have, be of a certain race than not? Or have a capital gain or a capital loss, or be employed for less hours. Like there's so many different things that can change based on those two things. So
And I just noticed that the relationship might also kind of hint at the gender.
yes, yeah,
Like husband
good.
probably is
Yes,
like,
indeed, yeah, it does, it does. That's
but
the
yeah,
tricky thing. You might want to. I didn't do that, but you might want to neutralize this by just putting spouse for husband and wife.
yeah, indeed. I was also when looking at the confusion matrices. It seems like the ratio, like positive and negative examples in the training set for males and females, is different, right? So because we have a lot more like true positives in one class, I
Oh
don't
yeah,
remember which one. Uh,
yeah.
yeah, this one, right? So I was wondering if we try to have balance, not class balance, but like ensure that the ratio is the same in
Yeah,
both.
you can do that.
Would it
Yeah,
be?
that's a it could be. That's a pre-processing method. You can take here it is. Hold on. What did I do with it? Um, yeah, you can do with this very same and there's other ways to do it, but you can definitely do upsampling or downsampling. to make sure that they're balanced. Like you could, if you downsampled, something you could do would be just take a percentage away from this one and a percentage away from this one and make sure they're on parity. So that this amount corresponds to 30% of this, right? And you might want to do it across both genders. So there's parity. 50% of the samples are males and 50% are females.
Mm-hmm.
That might be a good thing too. And that definitely would improve things.
Mm-hmm. And
The
this
thing
what
is, a lot of
we did
people
with
don't do that because they
something, right?
figure, well, what's that?
This is sort of what we did with giving weights, wasn't it?
Yeah, yeah. It's a way of doing it without having to do it.
Mm-hmm.
Um, a lot of people get kind of skittish as far as like doing like if they do downsampling, they're removing from their data and they might not have a lot of it.
Mm-hmm.
So you're removing potential predictive power from the data from the model by doing that. Um, if you upsample, you could be, kind of duplicating things that don't exist in your data, like kind of skewing the distribution.
Mm-hmm.
So it's kind of tough to do that and to figure out what's the best way of doing it. Um,
I guess the main takeaway from this for me personally is like when you have these protected features, we shouldn't just throw them away. We should keep them, and then we should use them for analyzing the performance of our model, right? So how fair it is. If we just throw it away, there is no way we can say, okay, our model is fair because we cannot check it, right? So simply not using the features does not mean that the model is fair.
no, no, because there's other things like you think by removing one feature you actually make the model fair, but there's other things in the data set that likely connect to that. So you would have to there's a pre-processing method that accounts for that and changes all the features that are connected to your feature. So it removes that feature. So it debiases the data set by modifying it. Um, and sometimes it's pretty severe, what it does, you know, as part of the process. Uh, my book gets into details about that one. I think it's in one of the examples. But yeah, um, it's definitely a tricky subject in the sense that there is not one method. There is not one way of doing this right. And it really depends a lot on what your outcome is, on what you want to do. And sometimes you have to explore, like here we did not explore race. Sometimes you have to explore race, you have to explore other things. Age, for instance, is one we did not explore, but it really depends on where you're not only you're finding the bias, but where your stakeholders are claiming to see bias.
So also it was, I guess it's tricky because when you try to debias the model, it may lead to uh, poorer accuracy. So the model becomes less accurate. And I'm wondering
Yeah.
like how to actually, um, the, like how do we balance bias here and accuracy? Like when we say it's okay for our model to be less accurate because we want it to be more fair, uh,
Yeah.
or we want the model to be more accurate. Like, what is better?
Yeah. Well, one way, I mean, there's many ways of doing that. I like the idea of making like a composite metric, a metric that is captures the essence of what it is to have high accuracy. Um, in this case, it could be it's not even accuracy, it's precision recall or one of them weighed more than another. So I'll do that. I'll say, well, what do we don't want to shoot precision down, like a cliff, but at the same time, we want to focus a bit more on recall. So we'll give like recall like a 70%. We'll say 70% recall, and so we'll create like an average between both, and then we'll take one of the the fairness metrics, and we'll weigh it in as well. So it's not something I have to come up with arbitrarily, but sit down with stakeholders and say, how much do you care about this? And then play around with that, because at the end of the day, we don't know till we see all the things like and see all the models like in a grid and say, okay, well, this one has this precision, this recall, and this amount of fairness, and so on. And kind of, you don't want to cherry pick it. You want to take like a fair look at that and like be objective as you can be. So it's tricky to kind of look at more than one metric, but it's sometimes the only way to do it. Because you want high accuracy, but you also want some, if not as much fairness as you can give, without making accuracy dip too much. So where is that threshold? It's yeah.
Okay, I guess that's all for today. Thanks a lot for joining us today. By the way, I also shared the link to to answers from Serg when we invited him to our book of the week, and you will find the links to the book, to the actual book there as well. So at the top. So check it out. There are amazing questions and answers. And again, thanks a lot for joining us today, for doing this workshop. That was really cool. And thanks everyone for attending the workshop, for asking questions. Maybe last one. If somebody wants to ask a follow-up question, what's the best way to find you?
They can find me on LinkedIn, on Twitter.
Okay. You shared this at the beginning, right, on the first slide.
It's also. Hold on. It is there. It is there.
Search.ai. Okay, great. Thanks a lot. Thanks again. I think that's all for today.
Sure thing.
Yeah.
Bye.